transfer using geostationary satellite, and how we can receive this kind of information using software-defined radio, our favorite software framework, New Radio, and consumer-grade satellite TV reception dish receiving the signal from the satellite. So before getting into the details of time and frequency transfer, let us just quickly define what is frequency and what is time. Frequency is this kind of boring signal where all the periods of the signal look similar to each other. So you've got the sine wave with its repetitive pattern, and if you look on the background at the spectrum, it's got a unique Dirac function because each period is similar to the neighbor. So if we want to introduce some sort of time information, what we can do is binary phase shift keying 1 out of 2 period by flipping 1 out of period, and by doing this we can separate 1 out of 2 period of a signal, and on the background you see that the spectrum has additional spectral components, but still our timing capability is quite poor. But we can generalize the concept by introducing a pseudo-random pattern of phase flipping, pseudo-random because we know what this pattern is, and by looking at the background spectrum, you see that now the spectrum has been spread because the unique pattern of phase flipping allows us to identify uniquely the time of flight of a signal. So you see the huge difference between frequency transfer and time transfer. Frequency is intrinsically a narrow band information, whereas time transfer requires processing broadband signals, and that's the big difference. Now, if we look at the self-similarity of the signal for the correlation function, we see here the cross-correlation between the received signal and the pattern calculated for a Fourier transform, and we see through this relation, the close relation between the autocorrelation, the self-similarity of the signal, and the power spectral density for the inverse Fourier transform. You see that a sine wave has no timing capability. All periods look similar to each other. By flipping 1 out of 2 periods, we improved a little bit, but not quite good. And by having the pseudo-random sequence, we have in the autocorrelation a Dirac function, meaning we have a unique time of flight estimate thanks to this spectrum spreading. So having introduced this topic, what we're going to do in all this processing is run this through software-defined radio, and the assumption will be that the A to D converter stream will have to be contiguous with a time separation between samples equal to the inverse of a sampling frequency. Any processing done afterward can be asynchronous, can be through buffer, through FIFO, as long as the A to D stream is contiguous. This will be our assumption that New Radio can provide us this contiguous stream. And the signal that we're going to analyze is generated by this commercial instrument initially developed in Stuttgart University, the SATRA modem, satellite time and ranging, now commercialized by the German company TimeTech. This is what we wish to, the signal we wish to investigate. So why actually are these timing signal exchanged between these various laboratories? So here you have a map of European metrology laboratories sharing their atomic clock signal to create Temps Atomique International, the atomic international time over here. And this comes from the definition, current definition of a second is 9 billion transition of a hyperfine transition of a cesium atom. So you have this generation of all these clocks in all these laboratories, and what they're doing is sharing this information to try to create an average of all these clock signals. Now, what are the requirements? To give you a hint, the speed of light is at the snail's pace of 300 meters per microsecond. So if you wish to meet some of the requirements, such as the MiFID regulation that says that for fast trading, each trade transfer must be timestamped within 100 microseconds with 1 microsecond resolution. If your bank or your trading center are located more than a few meters apart, then you need to have some sort of time transfer compensation because, of course, at 300 meters per microsecond, sub-microsecond resolution requires measuring the time of flight. 5G network, the difference between 5G and 4G is now that 5G is going to be time synchronous. The various stations of a 5G network must be synchronized to better than 260 nanoseconds, and smart grid for fault detection requires that the different installations are synchronized to better than 100 nanoseconds. So you see that with respect to this speed of light, we need a way of compensating for the time of flight of the signal. And the question is, can we use to our benefit these signals that are being broadcast by geostationary satellite between the observatories for synchronizing their clocks? Now, all the information I'm going to share with you are found in the public literature. You will find in the scientific publication the fact that these laboratories are sharing information as a binary phase shift keying with pseudo-random sequence modulation for time transfer. using the geostationary satellite Telstar 11N at 10.9 gigahertz carrier frequency. We're going to see this has changed a little bit with respect to the publication, that the broadcast signal is emitted every even UTC hour, and that each satellite signal, each broadcasting laboratory has a slight frequency offset as described in this PhD in French. So we have all the information about the signal that is being broadcast, and in our laboratory we have this 2.4 meter dish broadcasting the information during the even hours. But of course we don't want to use this very fancy hardware. We want to use our commercial off-the-shelf TV satellite reception dish, and the question is, can we use this hardware to receive a signal and to actually process the metrology information that are being broadcast using the SATRA modem by the various metrology laboratories. And by doing this, of course, we're going to process the IQ stream that have been recorded using software-defined radio, with the benefit that all stations will be processed at the same time, as opposed to the SATRA modem that can only process a single station at any given time. Now, if you want to do this in the US, over here on this side, you've got all the laboratories in Western Europe, and actually the selection of Telstar 11N was to allow communication in the US with NIST in Boulder, Colorado, with USNO in Washington, DC. And actually, even though the satellite is located 36,000 kilometers away, if you look at this 3D map, courtesy of Celestrak, you see that the signal is actually grazing. In Boulder, Colorado, the signal is only at 8 degrees above the horizon. In north of Europe, it's only 11 degrees. From our location in Besançon, it's 21 degree elevation, but at the east-west German border in Braunschweig, PTB, it's only 16 degrees. So you see that your satellite dish is going to be looking quite close to the horizon. So if the first thing we want to do is to receive this microwave signal, we need to understand how the LNB, so the low noise block that is located at the focal point of your satellite dish, is working. The LNB is converting the microwave signal, downlink 10 to 13 gigahertz, using the local oscillator and some microwave preamp, IF preamp, to a more reasonable gigahertz signal. If you look here at the spectrum that I recorded, this is the frequency range of a signal that you can receive, and this is the leakage of a local oscillator at 975 gigahertz, that's this guy over here. Now, of course, these components have to be powered, so you need a bias T. The bias T will be fed using 13 to 18 volt DC power, depending on the polarization. 13 or 18 volts will make you flip from horizontal to vertical polarization, and you feed your software-defined radio with the output signal, making sure that the capacitor here blocks the DC signal from damaging your software-defined radio front end. If additionally you inject 22 kilohertz, you can shift the local oscillator from 975 gigahertz to 10.6 gigahertz, extending the frequency range of operation of your LNB. Now, indeed, what is the frequency of a signal we wish to receive? And to know this, we've got this invaluable information from the BIPM, Bureau International des Poids et Mesures website, that gives you all the information about the frequency and the operating conditions of the various batteries. On top over here, you've got this file from OP, Observatoire de Paris, where they tell you that the reception signal is, the received signal is at 10.95 gigahertz for the European broadcast, and that the signal is at that's for European broadcast. For the US broadcast is at reception at 11.5 gigahertz. This is the information for NIST in Boulder, and this is information for USNO. So you see that the American link is slightly at higher frequency than what we have in Europe, and then you can benefit from this higher frequency operating of LNB by shifting to 10.6 gigahertz, making your software-defined radio operate at 1 gigahertz instead of 1.7 gigahertz. So once we know what the frequency band is, why actually do we need in the laboratory this 2.4 meter dish when a 60 centimeter dish can be used? Well, of course, by using the 60 centimeter dish instead of the 2.4, we're losing a bit of gain, 12 dB gain. But the most striking reason for using 2.4 meter dish is that we are transmitting, we're not only receiving in our laboratory. And what the regulation tell you, and this is documented in this in this information here from the EUMETSAT, how the design requirement of a very small aperture terminal is that when you're transmitting, you must make sure that your broadcast signal is only illuminating the targeted satellite and not the neighboring satellite. But however, what you see over here is that the geostationary orbit is completely crowded. There's one satellite every half a degree. And so if you want to make sure that your beam width is less than half a degree wide at 14 gigahertz uplink, well, actually a quick calculation tells you that you need a 2.4 meter dish. And once you've realized why the 60 centimeter dish will be sufficient for receiving your broadcast signal, well, what you're left with now is knowing how to point your satellite. We're going on the dishpointer.com website. You give it your location, you give it which satellite you want to work with, and they will give you azimuth elevation. Be aware that when I started this project, elevation is easy to set, but I was mistakenly aiming at the wrong satellite, and if of course you're looking at the wrong satellite in azimuth, then you will not get the signal that you're looking for. So be sure that you look a bit around around the azimuth. So once we've received our first signal on the carrier, the first thing you know from the publicly available literature is that each laboratory is broadcasting with a slight frequency offset in addition to the binary phase shift keying BPSK. So the first thing we want to know is what is the frequency of the received signal, and as usual with radio frequency communication, we need to compensate for frequency offset. So for BPSK, what you need to do is square the signal, because by squaring the signal, you get rid of a spectrum spreading introduced by the phase modulation, and you collapse all the energy in the carrier. So here you see the various carriers on top received at different times. So the frequency is shifting over time, and on the bottom here we've realigned the spectra just by shifting the frequency multiplying by local oscillator. Indeed, here on the right you see over a few days, 2 days, this is the frequency offset of a few hundred hertz introduced by the satellite transponder as it is converting the uplink 14 gigahertz to the downlink 11 gigahertz. So compensating for this frequency offset is a mandatory requirement before BPSK demodulation. So now that we have a signal that is located on 0 hertz for frequency offset, we need to identify the code that is encoding each transmission. Now, the precursor of the Sartre modem was the development by Hartl at University of Stuttgart of the Mitrex, and that's the only public information that you will find. There is no public information on the Sartre modem. And if we search for Mitrex, you see here the various information that was published in 1986, and they tell you that the pseudo-random sequence is a 14-bit shift register truncated to the decimal value of 10,000 bits. So remember, this was developed end of the 70s, in the 80s, at the same time as Globalstar that became GPS. So you don't expect any very fancy modulation scheme. What we're going to look for is linear feedback shift register using Galois algebra on the 14-bit sequence truncated to 10,000 bits. And luckily enough, a brute force approach tells us that there's only 756 maximal length possible solutions of 14-bit shift register, and they're all listed at this Carnegie Mellon University CMU website. So we can have a brute force approach where we actually test all possible codes for each possible frequency offset. So you see here the squared BPSK signal with the various frequency offsets associated with each laboratory, because squaring the signal will take the double of the argument. Taking the double argument collapses all the energy into the carrier. So that's what you see over here. And for each one of these frequency offsets, we run all the correlation with all possible codes. And in this case, by looking at the correlation peaks in the y-axis, in the x-axis is the code index, you see that actually the orthogonality is not so good, because some sequences have multiple codes that match their sequence, but still we can identify for each observatory, because we know that each one of these frequency offset is associated with one observatory, we can find a unique code. So we've identified each code associated with each observatory, and now we can try to time the signal by looking at the correlation peak location as the signal is being broadcast. So this gives us the outline of a processing step that we wish to follow. Just be aware that depending on the implementation that you're using, whether it's a Galois linear feedback shift register or a Fibonacci linear feedback shift register, this is the C code you'll find on Wikipedia. This is the MATLAB code that you'll find on MATLAB Central. They will generate the same sequence, except that they have different time offset, which is what you see over here. But anyway, since we did not know what the initial seed was, 0 is a all forbidden state, because 0 XOR 0 gives you 0. So we started with a quite obvious solution of all ones. And by looking between Fibonacci and Galois, you see that you get different time offset, but the truncation of 10,000 bits over the 16,000 will still give you 60% overlap, even if you take the wrong starting point. So whether you're taking Fibonacci or Galois, you will still have a correlation peak. So this is the outline of our processing sequence. We start by compensating for the coarse frequency offset by squaring the signal. And why actually do we have this frequency offset? This is your metrological clock. So this, you know, is perfect, but you have no idea, you have no clue how there is up conversion. You have no idea what's happening here on the satellite with a transponder transposing from 14 gigahertz uplink to 11 gigahertz downlink, and you don't really know what's happening here in the LNB. So necessarily your software-defined radio and post-processing will need to compensate for this coarse frequency offset that you find by squaring the signal. Or if you don't want to do it manually, you can take new radios, Costas loop with an order of 2, because we're talking about BPSK, binary phase shift keying, that will compensate for the frequency offset. Once we've compensated for frequency offset, we interpolate the code to the right sampling frequency. Now the chip rate can be known by looking at the spectrum of the BPSK. We know that the first notch is located at the chip rate. In this case, 2.5 megahertz, so 2.5 megachip per second. So since we record the data using software-defined radio at 5 megahertz, we need to interpolate by a factor of 2, which is easy enough. Just duplicate each bit. And if we have 10,000 bit-long sequences at a 2.5 megachip per second, we expect a correlation peak every 4 milliseconds. And we repeat this, whole data set of about 2 minutes will hold about 3.6 gigabytes, but there is no need to process the 4 gigabytes in one run. We actually split the file as pieces of 20,000 samples, 20,000 because the ratio of the sampling rate to the chip rate is 2, and we know that there is a single correlation peak every time we correlate this IQ sequence with pseudo-random sequence. And this is your classical code Doppler shift map that you're familiar with for GPS processing, where the background color blue is no correlation, yellow is a strong correlation, and we actually find the code for each observatory over Western Europe with, in the x-axis, the various frequency offsets. And you see that the 1800 hertz on the bottom of the chart is the frequency offset that has been introduced by the transponder on the satellite over here with respect to its nominal frequency. So now that we've got these correlation peaks, this is typically what you will find. So as the 3 minutes of the record is evolving, you've got here the correlation time delay. So the sampling rate of 5 megahertz will give you 200 nanosecond resolution. You see that here we have much better than 200 nanosecond. This is achieved by a linear polynomial second order parabola fit of a correlation peak. And you see here that we have much better than the 200 nanosecond standard deviation. And every beginning of a second starts with a jump in the time. Now, this jump is not very well defined. You see various definitions in the literature. In this PhD over here, there is a definition in terms of time of flight. In this paper by Hartle, they tell you it's a phase shift of 90 degrees. And actually, when we look at our own Mitrex SATRA modem, we just see that the transmission stops at the beginning of each second. So it's not really clear what this jump is, but it defines the beginning of each second, so the absolute time of beginning of each second. And this jump we're going to get rid of when we estimate the accuracy of the time of flight. So we never here look at absolute time of flight, we look at relative time of flight, so between one observatory and another observatory. So we've got the broadcast signal by these various observatories, and we are recording with our parabola dish the software-defined radio receiver sequence, and we process this received signal using the software-defined radio reception. And what you see here for 8 observatories, you see the time of flight difference with a standard deviation in something like the 10 to 11 nanosecond time of flight difference, which gives you, so that's 10 to 11 nanosecond over 3-minute record. That gives you an idea of what is the accuracy with which we can detect the time of flight. Now, if you're familiar with GPS, you know that GPS is broadcasting the unique code associated with each satellite. That's CDMA, code division multiple access. And in addition, there's the navigation messages that are being broadcast. Now, in the Mitrex publication, they don't tell you anything about the digital communication, but we might think did SATRA with TimeTech technology add an additional digital sequence. So what we did here is, this is the phase evolution over time. And if you take double of a phase because it's changing between 0 and pi for BPSK, you unwrap this double phase, so that's your continuous phase evolution. You can subtract this double phase from the received signal, and by doing this, you actually observe that the real part is flipping between +1 and -1. +1 because cosine of 0 is +1, -1 because cosine of pi is -1, and indeed you see that after removing the pseudo-random sequence, we still have this phase flipping on the correlation output. Remember, correlation is a linear operation, so any phase introduced on the transmitted code will be detected on the output of a correlation. And if we look at the autocorrelation of this bit sequence, we see that there is a peak at 250 hertz, which tells you that some sort of digital pattern is repeated every 250 bits, which actually makes sense because 250 bits is inverse of 4 milliseconds. So this means that each bit is encoded by one of the correlation outputs. So if we reorganize the output of the BPSK sequence after removing the slow phase drift, what you see over here is actually, so you reorganize 250 bits. These are the charts with the fast time axis in the X. You see the slow time axis over the Y over here. And so this tells you what the sentence looks like and how the sentences repeat. So indeed, there is some repeated pattern. In this case, for 9 observatories, we were not able to decode the message. You obviously here see that there is some sort of header, then a message, then a footer, but we were not able to decode the payload. This is still work in progress to try to detect what is the digital message that is being broadcast by SATRA modem. Actually, in the documentation of a SATRA modem, you find a hint about these high rate data messages. We were not able to find any forward error correction encoding scheme. So at the moment, we know that there is a digital message for transmitting this correction information between SATRA modem, but we don't actually know what is the payload of these messages. Now that we know how we can decode the messages, are we actually able to do a use for the one-way reception of this information by looking at these signals using our parabola dish? Of course, we're not allowed to broadcast, so we cannot compensate in a two-way fashion. And remember, the requirement that we're looking for is something like 100 microseconds for MIFID. We're looking at 100 nanosecond to compare with GPS, or actually even nanosecond for GPS with phase. Temps atomique international requires time of flight much better than 1 nanosecond. And if you look at the record that we did using our satellite dish, so here we have a B210, and the B210 was triggered by the 1 PPS output of a GPS receiver. Now, be careful that if you look on the internet, Paul Boven's code example was using a trigger with a delay much bigger than 1 second. The API of UHD must have changed because now you must delay by much less than a second to trigger the B210 recording, but this is what we did. And if you look over here, this is the evolution of a correlation peak that was received using a satellite dish, and due to the motion of the satellite around its equilibrium position, you see that the time of flight varies by something like 150 microseconds, which is 50-kilometer motion of a satellite around its equilibrium location. So the question is, can we detect the motion of a satellite and we compensate for it? So the first idea is to say, let's try to take two dishes and to look at the time of flight difference between introduced by the motion of a satellite. Now, if you put these two dishes at a separation of 3 meters, you realize that when the satellite moved by 30 kilometers at a distance of 39,000 kilometers, the time of flight difference is only going to be a few picoseconds, and this is beyond what we can detect. How do we increase the time difference when we need to actually increase the baseline, which is classically done in radio astronomy? But this becomes impractical in a local situation. So actually, what can we do? Well, we can benefit from the fact that all these observatories are located around Europe, and Europe will give you a baseline of about 1,500 kilometers. So this is why I call this GPS upside down. You've got this high timing of accuracy information broadcast by the satellite, by the meteorology laboratories, and received by your satellite, and we can try to compensate for the time of flight by measuring the difference. So this is an example of a measurement that we did for the various observatories. So you see here Spain in Cadiz, you see Torino in Italy, and you see that we match very well our measurement with the BPM files. So this is the pink line over here was collected on the BPM website, and you see that we match very well. And the question is, can we collect the data from the observatories, broadcast through Telstar 11N, received by our satellite dish, and can we compensate for the motion of a satellite by looking at the phase difference introduced on the various observatories? Now, just be aware that when you're doing this, you need to make sure that you interpolate correctly the measurements, because SATRA modem is only able to look at a single satellite broadcast at any given time. And what you see over here is actually that Paris is broadcasting at hour plus 7 minutes, PTB is broadcasting at hour plus 19 minutes, and if you just look at the results, the time of flight doesn't look very good because the satellite has moved in between. If you interpolate, because our software-defined radio processing looks at all the data simultaneously, then you've got this excellent match, whether with PTB, whether with INRIM in Italy, but you need to interpolate so that all the measurement times are at the same time and not delayed as is done by the SATRA modem. So now that we know how to look at the time of flight, this is no longer the absolute time of flight, this is the relative time of flight. So you see it's much less than 150 microseconds because all the observatories located in Europe look at the satellite in the same direction. So actually the motion of a satellite introduces a much smaller time difference, but this is the expected time offset difference due to the motion of a satellite in the X direction, Y direction, or in altitude Z direction introduced. So this is what we need to compensate for if we wish to be able to have high accuracy timing using one-way communication. And so you see that the problem is not well organized because all the observatories are broadcasting over the satellite located over the Atlantic Ocean. But if you look at the evolution of this position estimate over time, you see actually the motion of a satellite. Bottom right is in the Z direction, on the left is in the XY plane, and here you've got the motion of a satellite. So here the accuracy is much below what is targeted for sub-microsecond timing accuracy, but still by analyzing this time of flight difference, we can see the satellite moving in space by looking at the phase introduced between the various observatories. So with this, I conclude my presentation showing that we've been able to receive broadcast time and two-way time and frequency signal transmitted by Telstar 11N and received using our TV reception antenna. You see that we've been able to develop a processing framework that you can get over here on the GitHub website, and this might be a complement to GPS time and frequency dissemination since there's a lot of issues with jamming and spoofing of GPS at the moment. You see that the targeted accuracy is in the 10 to the minus 9 divided by the integration duration, and current work in progress is to improve the resolution with which we detect the position of a satellite, possibly correcting for the motion of the Earth as the satellite is being, the signal is being broadcast from ground to space, and trying to decode the digital message. With this, I thank you for your attention.